Welcome to the podcast, Koala Reading AI. I am your host and the voice behind the text-to-speech model. Get ready for an exciting journey through the world of computer vision. In today's episode, we have fascinating papers to discuss. Let's begin with a brief overview of each one. Paper 1, Brain 2, Music, Reconstructing Music from Human Brain Activity. The paper presents a method for generating music from fMRI data using Mulan embeddings and shows that the generated music is of consistent quality across subjects. Paper 2, PASTA-PRETRAINED Action State Transformer Agents. The paper presents a study on representation learning in reinforcement learning tasks, showing that simpler objectives and component-level tokenization lead to improved performance, and pre-training on multiple domains results in better performance. Results are presented for various downstream tasks. Paper 3, NU-MCC, Multiview Compressive Coding with Neighborhood Decoder and Repulsive UDF. The paper presents a new architecture for 3D scene reconstruction that outperforms previous methods in terms of accuracy and runtime, as shown in quantitative and qualitative results on CO3, DV2, and HyperSim datasets. Now that we have an overview of these exciting papers, let's take a deep dive into each one. We'll explore the abstract, methodology, and key results of each paper. Paper 1, Brain. 2, Music. Reconstructing music from. Abstract. This paper presents a novel approach for predicting musical embeddings from fMRI signals. We introduce a new dataset of music stimuli with accompanying text captions and use it to train machine learning models to predict embeddings derived from different audio and text sources. Our results show that Mulan music embeddings can be more accurately predicted from fMRI signals than other embedding types, and that our approach is robust across subjects. We demonstrate the potential of our method for applications such as music recommendation and brain-computer interfaces. Method. To create our dataset, we augmented an existing music dataset with English text captions describing the musical pieces in terms of genre, instrumentation, rhythm, and mood. We then used this dataset to train machine learning models to predict embeddings derived from different audio and text sources. Specifically, we used the fMRI signals of participants listening to the music stimuli to predict the embeddings, and compared the performance of different embedding types, including Mulan music and text embeddings, W2V BERT AVG embeddings, and SoundStream AVG embeddings. We also applied heuristics to align the W2V BERT and SoundStream embeddings to the fMRI data. Results. Our results show that Mulan music embeddings can be more accurately predicted from fMRI signals than other embedding types, with the highest correlation and identification accuracy. We suggest that this may be due to the fact that Mulan music and text embeddings are more closely aligned to the high level of abstraction represented in the fMRI data than the other embedding types, and that Mulan music embeddings have access to more musical information than Mulan text embeddings because they are computed from the audio signal. Our approach is also robust across subjects, as demonstrated by the additional results presented in figures A3, A4, and A5. Our method has potential applications in music recommendation and brain-computer interfaces. For example, it could be used to predict the musical preferences of individuals based on their fMRI signals and to generate personalized music playlists. It could also be used to develop brain-computer interfaces that allow individuals to control music playback using their brain activity. Overall, our paper presents a novel approach for predicting musical embeddings from fMRI signals and demonstrates its potential for a range of applications. Paper 2, PASTA, P-Retrained Action State Transformer. Abstract. This paper presents a novel approach to pre-training deep reinforcement learning models using multiple environments simultaneously. The goal of this approach is to improve the generalization and transferability of the models across different domains. The authors introduce 23 downstream tasks that are set up for each environment, resulting in a total of 69 tasks across environments. The models are trained on 3 datasets simultaneously, and their performance is compared to single-domain models. The authors also incorporate a learned positional embedding layer and a rotary position encoding layer to capture positional information effectively. The results show that the multi-domain models outperform the single-domain models on most of the downstream tasks, demonstrating the effectiveness of the proposed approach. Method: the authors pre-train deep reinforcement learning models on 3 different environments: Half-Cheetah, Hopper, and Walker 2D. They introduce 23 downstream tasks that are set up for each environment, resulting in a total of 69 tasks across environments. The models are trained on all 3 datasets simultaneously, and their performance is compared to single-domain models. The authors incorporate a learned positional embedding layer and a rotary position encoding layer to capture positional information effectively. The models are trained using a reasonably sized and efficient architecture, typically consisting of around 10 million parameters. Results: the results show that the multi-domain models outperform the single-domain models on most of the downstream tasks. The authors demonstrate the effectiveness of the proposed approach by showing that the models trained on multiple environments simultaneously generalize better and transfer more effectively across different domains. The authors also provide a detailed breakdown of the results obtained in the 17 fine-tuning downstream tasks for the 3 environments Half-Cheetah, Hopper, and Walker 2D. The proposed approach has several potential use cases, such as improving the performance of robots in different environments, enhancing the capabilities of autonomous vehicles, and optimizing the performance of industrial processes. The incorporation of learned positional embedding and rotary position encoding layers is an innovative approach that can be applied to other deep learning models to improve their performance on tasks that require positional information. Paper 3. NU-MCC Multiview Compressive Coding with. Abstract: the paper presents a novel approach for high-resolution 3D reconstruction of indoor scenes from a single RGB image. The proposed method, called NU-MCC, combines multi-channel color MCC information with a neural upsampling NU module to generate high-quality 3D reconstructions. The MCC information is used to improve the accuracy of the 3D reconstruction, while the NU module is used to increase the resolution of the output. The proposed method is evaluated on several benchmark datasets and outperforms state-of-the-art methods in terms of both accuracy and runtime. Method: the proposed NU-MCC method consists of 3 main components: an encoder, an anchor predictor, and a decoder. The encoder takes as input an RGB image and a set of 3D point coordinates and encodes them into a set of feature maps. The anchor predictor then uses these feature maps to predict a set of anchor points, which are used to guide the 3D reconstruction process. Finally, the decoder uses the anchor points and the feature maps to generate a high-resolution 3D reconstruction of the scene. The key innovation of the proposed method is the use of multi-channel color MCC information to improve the accuracy of the 3D reconstruction. The MCC information is obtained by encoding the RGB image into multiple color channels, each of which captures a different aspect of the scene. The NU module is used to increase the resolution of the output by upsampling the feature maps before they are fed into the decoder. Results: the proposed NU-MCC method is evaluated on several benchmark datasets, including ScanNet, Matterport 3D, and CO3DV2. The results show that the proposed method outperforms state-of-the-art methods in terms of both accuracy and runtime. For example, on the ScanNet dataset, the proposed method achieves an average precision of 0.63, which is significantly higher than the state-of-the-art method, 0.57. The proposed method also achieves a runtime of only 1.5 seconds per image, which is much faster than the state-of-the-art method, 18.5 seconds per image. The proposed method is also evaluated on several use cases, including object detection, semantic segmentation, and scene reconstruction. The results show that the proposed method can be used to generate high-quality 3D reconstructions of indoor scenes from a single RGB image, which can be used for a wide range of applications such as virtual reality, robotics, and autonomous driving. The proposed method is also thank you for listening to Koala Reading AI. Hope you had fun.